All right, today we're talking about spontaneous reactions. Now, I don't want you to get the wrong idea about what a spontaneous reaction is, because what you may be thinking is, oh, spontaneous combustion means that something just goes poof and just bursts into flames. That's spontaneous combustion. That's not exactly what spontaneous means in terms of a reaction. If a reaction is spontaneous, what that means is that once you get it started, because if you remember from our energy diagrams of the reactions, every reaction requires a little bit of energy to get it started, and we call that activation energy. So beyond the activation energy, will the reaction keep on going without having to continually supply more energy to the reaction? Or once you get it going, will it just go on its own? And so when I talk about a spontaneous reaction, that's what I mean. Will it continue on its own without my having to continually add more energy to keep it going? Well, in order for a reaction to be spontaneous, it has to obey the second law of thermodynamics. Now remember, the second law of thermodynamics said that the entropy of the universe can never decrease. It always either has to stay the same or it has to increase. So let's think about what that means. If my delta S is positive, that means that the disorder in the system, the entropy of the system, is increasing. But I also have another factor that we've talked about. So we've talked about entropy, but we also talked about enthalpy. If the enthalpy of a particular reaction is negative, what that means is that it's giving off energy to the surroundings. When it does that, the surroundings, the temperature of the surroundings is going to increase, and so that means that the entropy of the surroundings is going to go up. So therefore, if my delta H for a reaction is negative, the entropy is going to increase. So if I have a particular reaction where in combination the delta S is positive and the delta H is negative, I know that that reaction is going to be spontaneous. It will take place because it is obeying the second law. It is increasing the entropy of the universe. I can actually combine my delta S and my delta H into another function, state function called G, which is called Gibbs free energy. And Gibbs free energy, again, is a combination of my enthalpy and my entropy, and it also takes temperature into consideration. Now, this temperature must be expressed in Kelvin. And because, as you can already see, signs are so important here. If you're using a temperature in anything else, the temperature could be, if you used it in Celsius, you could have a negative temperature, and then that's going to really mess with your signs here. So you need to put a temperature in that's always positive, and the only way to do that is to use the temperature in Kelvin. So when you're using this particular formula, make sure that you're putting your temperature into Kelvin. So now let's look at what the dynamics of this equation actually look like to use them. We already said that if the delta S is positive, so if I take a positive delta S times a positive Kelvin temperature, this number over here will be positive, okay? If my delta H is negative, I'll have a negative number minus a positive number, which will give me a more negative number. So what that tells me, I already know the reaction spontaneous if delta S is positive and delta H is negative. So if this is positive and this is negative, the result means that delta G is going to be negative. And so what happens is that if my delta G is negative, my reaction will be spontaneous. Again, spontaneous meaning that once you get the reaction started, it will continue on to completion without your having to add any other energy to the system. If it comes out that the delta G is positive, then the reaction will not be spontaneous. So there's several different situations that I can look at here to determine if my reaction is going to be spontaneous or not. So as we've already said a couple different times, if my delta S is positive and my delta H is negative, that is going to give me a negative delta G, which means the reaction will be spontaneous. Now, let's think about what happens if my delta H is positive and my delta S is negative. Well, if delta S is negative and this is positive, I'm going to have a negative number here. Well, subtracting a negative number is the same as adding a positive number. If the delta H is already positive, and then I'm subtracting a negative number, making it more positive, that means that my delta G is going to be positive. And so that means that this type of reaction will not be spontaneous. Okay, so delta H is negative, delta S is positive, it is spontaneous. Delta H is positive, delta S is negative, reaction is not spontaneous. That's pretty straightforward. What happens if delta H is negative and delta S is negative? Well, a negative times a negative makes a positive, so at that point it depends on how big of a positive number this turns out to be if this one's negative. I'm going to have the same type of situation here. If delta H is positive and delta S is positive, I've got a positive number minus a positive number, but which one of them is larger? Until I actually have numbers to plug in there, I don't know. And so here, I don't know if the reaction is going to be spontaneous, and I actually have to have numbers to plug in there in order to determine if my reaction is going to be spontaneous or not. Now, just as you've already seen for, just like we used Gibbs law, not Gibbs law, we used Hess's law. We used Hess's law to determine enthalpies for reactions for enthalpy. We were also able to use Hess's law to determine the entropy of a reaction. For that, we can use Hess's law here as well too, as long as you have some statements of a chart of what the Gibbs free energy is for specific compounds, okay? So you can use Hess's law. What I'm going to show you today is where we're going to use this relationship to figure out whether a particular reaction is going to be spontaneous. And as you can tell, but just by looking at this, it's based on what the temperature is for that reaction to take place. So let's create some more space here. And we will look at a couple of example problems. So if you have your sheet that has all the example problems on it, that's what I'm going to be looking at here. So the first problem is that we use the chemical reaction 2NO plus O2 yields 2NO2. We have the delta H and we are given the delta S, and so we want to know what the delta G will be at 532 degrees Celsius or 805 Kelvin. Is it spontaneous at that particular temperature? Because temperature matters. So what I'm going to do is I'm going to use this delta G equals delta H minus T delta S, and I'm going to use the equation or use the information that they gave me in order to determine if the reaction is spontaneous or not. Now, one thing that you have to watch when you do this is that enthalpies are usually given in kilojoules, whereas entropies are usually given in joules. And so since we have a subtraction sign in here, we have to make sure that we convert so that we're using joules in both of them. So since they told you it was 114.2 kilojoules per mole, I'm going to convert that into joules. So my delta G is going to be negative 114,200 joules per mole. I'm going to subtract the temperature. Remember, we have to use the Kelvin temperature, which is 805. And then the delta S that we were given is a negative 147 joules per mole Kelvin. And so the Kelvins are going to cancel out, and I'll have joules per mole in both of these terms here. And when you actually calculate that, again, be very careful as you type these into your calculator to make sure that you make things negative and hit subtraction signs when you're supposed to. Okay, so here it turns out that my delta G is going to be 4135 joules per mole. Now, with what we've already discussed, this is a positive number, and so what that tells me is that this reaction will not be spontaneous at 805 Kelvin. Okay, so then the question becomes, is there a temperature at which it would become spontaneous? Because we said temperature matters. And so I know that in order for this reaction to take place, delta G has to be negative. So if I want this to be negative, what that means is that delta H minus T delta S has to be less than or equal to 0. I'm sorry, it has to be less than 0. Has to be less than 0 so that the delta G will be negative, okay? So I know delta H, so I'm going to go ahead and plug that in, negative 114,200 joules per mole. That got a little messy. Joules per mole. I'm trying to find out what the temperature would be to make it spontaneous. So I'm going to put in T, and then I have negative 147 joules per mole Kelvin here has to be less than 0. Okay, so the first thing I'm going to do is I'm going to take this and I'm going to move it to the other side. When we add and subtract with inequality signs, we don't have to do anything about the inequality sign. I'm just going to add 114,200 to both sides. So what that does is that gives me negative T times negative 147 joules per mole Kelvin is less than a positive 114,200 joules per mole. Okay? Then what you see is that I have a negative number times a negative number, and a negative times a negative makes a positive, right? Okay, so now since I've got all positive numbers, I can divide both sides by this 147 joules per mole Kelvin, and I'll divide this side by 147 joules per mole Kelvin. And so here everything cancels out, and so what I'm left with is that T, the temperature has to be less than 777 Kelvin in order for this particular reaction to be spontaneous. Okay, so as long as the temperature is less than this, the reaction will proceed on its own. It will not proceed on its own if the temperature gets too high. Okay, let's do one more example where we have to really watch what we do with that inequality sign. So once again, we will get rid of this and make a little bit more space. The next sample problem I gave you says the delta H of a certain chemical reaction is 10 kilojoules, whereas its delta S is 123 joules per Kelvin. At what temperatures is this reaction spontaneous? Okay, so again, just like I did before, I know that in order for this reaction to be spontaneous, delta H minus T delta S has to be less than 0. Okay, so I need to convert the delta H so that I have it in joules. So that's going to be 10,000 joules per mole. And I'm going to subtract T times the delta S. In this case, it's positive. So I have 123 joules per mole Kelvin, and it has to be less than 0. Okay, so the first thing I need to do is move this to the opposite side. So I'll have a negative T 123 joules per mole Kelvin is less than a negative 10,000 joules per mole, because obviously I moved this to the other side, so it's now going to be negative. I'm going to divide both sides by a negative 123 joules per mole Kelvin because I need to get rid of this negative sign, so I have a positive T left. And I'm going to divide this side by a negative 123 joules per mole Kelvin. When you divide or multiply either one of those by a negative number and you're using an inequality sign, you have to take that inequality sign and you have to flip it the other direction. So make sure you don't forget that particular piece from your algebra, because if you don't flip it, you're going to end up with a really wacky answer. Okay, so when I divide that, this T becomes positive, and then my temperature becomes 81.3 Kelvin. So for this particular problem, as long as my temperature is greater than 81.3 Kelvin, which is a very low temperature, by the way, as long as it's greater than that, the reaction will be spontaneous. Okay, so as you are working these problems, if they tell you to use Hess's law, make sure that you do it that way, but there will be other problems where you're going to be determining at what temperature something will be spontaneous, and at that point you have to use this particular method. So make sure that you're very careful watching your negative signs and flipping that inequality sign when it's necessary.